So let's see how we're going to go about graphing polar curves. And here by polar curves, we mean curves with this kind of equation, r equal f of theta, even though we could consider more general types of equations that relates r and theta. But for now we're going to focus on that. R here, of course, is the distance to the pole, possibly sine distance to the pole because we admit negative values for r. And theta is the angle between the polar axis, or positive x-axis, and the half ray that joins the pole with the point of coordinates r theta. Example of polar curves that we're going to discuss in this video include the curve r equals sine 2 theta, r equal 1 minus cosine theta, and r equal root 3 over 2 plus sine theta. Other polar curves that you're going to study in the sample quiz include r is sine of half of theta, r is half of theta, or r is sine 5 theta. And if you plug these curves into a grapher in polar coordinates, what you would obtain for the first curve would be something that looks like this. For the second one, you would get this curve, forgetting about the unit circle that is represented as well here. And for the third one, a curve that looks like that, where you have a little loop near the pole. And these three curves are curves that we're going to study, so we're going to see how we obtain these graphs. As for the other three, as I said, these are things that you would study in the sample quiz, and you'll see the solutions to obtain these curves. For the first one, you could get something that looks like that. R equals theta over 2 would be a spiral that looks like that. Again, we have the unit circle represented on that graph. And for the last one, you would get something with 5 loops all joining at the pole. So you see that we get a variety of different curves, interesting looking curves, and we're going to talk about how do we go about sketching these things if we don't have a grapher to do it for us. So let's start with a polar curve r equals sine of 2 theta. One important idea to understand about the method we're going to talk about to sketch this kind of curves is that we're going to look at this curve in two different sets of coordinates. First, we're going to look at the graph of the function sine 2 times an angle. So in other words, we're going to trace r equals sine of 2 theta in the Cartesian coordinates theta r. In other words, we just look at the graph of the function. So it's like y equals sine 2x, except that the first coordinate is not x but the angle theta, the second coordinate is not y but r. So this, of course, does not correspond to the polar curve. It just gives us a variation of r in terms of theta. There are important pieces of information on this graph that we're going to use to draw the polar curve corresponding to this equation. In particular, at these values of theta, for theta equals 0, pi over 2, pi, 3 pi over 2, or 2 pi, and other multiples of pi over 2, twice the angle is a multiple of pi, and therefore its sign is 0, which means that r is 0. In other words, for these values of the angle, theta, r is going to be 0, that means we're going to be at the pole. Other important points on this graph are the values of theta where r takes extremal values. Either its maximal value 1 or its minimal value negative 1. And this happens for the values of theta, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, because when we multiply by 2, we get pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, which when plugged into the sign gives us either 1 or negative 1. So now we are going to look at what it means in the xy plane, not the theta r plane, in the xy plane in which we look at the corresponding polar system of coordinates. So we have this polar grid, and we're going to try to trace what happens along the curve r equals sine of 2 theta. The circle that is drawn outside is a unit circle, and this is going to be a limiting curve because r, which is the distance between a point on the curve and the pole is at most 1 in absolute value. That means we are always going to be inside the unit disk. So let's try to follow the curve on the top, the graph of the function, and follow what it means geometrically when we are in polar coordinates. Let's start with theta equals 0 and then r is 0. That means we are at the pole looking in the direction of angle 0 with the positive x-axis. So we are looking in the direction of the positive x-axis and we are at the pole. And then we're going to look at what happens as the angle theta increases from 0 to pi over 4. So this direction in which we look is going to change, going towards pi over 4, and as we do that, the distance to the pole increases. In other words, the red point is going to move along this blue half ray, moving away from the pole as the blue half ray turns from angle 0 to angle pi over 4. And the red point this way traces out a piece of the polar curve corresponding to this interval from 0 to pi over 4 for the angle theta. So now we've reached the maximal value of r, which means we are at the point furthest away from the pole. And you see that when theta is going to go from pi over 4 to pi over 2 now, r is going to decrease. So if I continue to turn from pi over 4 to pi over 2, r decreases. That means I go back towards the pole, and for the angle pi over 2 I'm going to be back at the pole. Again, the red point is tracing out the corresponding part of the curve, going towards the pole as we're turning in terms of the angle. So now I'm at the point corresponding to theta equal pi over 2. And you see that when we're going to continue to turn, when this blue half ray is going to continue to turn from pi over 2 to 3 pi over 4, now r is negative. That means that the corresponding red point is not going to be on that half ray, but on the half ray on the opposite side. So I'm going to draw it on the opposite side, and as I continue to turn from pi over 2 to pi over 4, the red point is going to move away from the pole, but on the opposite half ray, on the other side, just like that. And it's tracing out the corresponding part of the curve. And now I'm at the point furthest away when I'm on the opposite side of the direction that I'm pointing to, and from 3 pi over 4 to pi, as the positive half ray turns from 3 pi over 4 to pi, the opposite one is going to go towards the positive x-axis, and r is going to decrease from this maximal value back to 0, in other words, back to the pole. So this is what we get, and again we trace out the corresponding part of the curve. Now we're back at the place where theta is pi, and now when we continue to turn from pi to 5 pi over 4, the angle is positive again. I'm sorry, r is positive again, so we are moving along the positive direction. That means I can erase this other side, and I'm going to look just at the direction in which I am pointing. So if I do that, I'm going to move along again towards the point where r is maximal. I'm at distance 1, and then from 5 pi over 4 to 3 pi over 2, it's decreasing back to 0. At this point, r is going to become negative again between 3 pi over 2 and 2 pi, so I'm going to look at what happens on the other side, and my red point is going to move along that opposite half ray, tracing out a piece of the curve as the direction in which I am pointing moves from 3 pi over 2 to 7 pi over 4, but of course the red point is on the opposite half ray. And again, if I continue to turn towards 2 pi, then on the opposite side the red point is going to go back towards the pole, completing the curve this way. Okay, so we have a rough sketch of what happens as theta makes a full revolution. Of course, to get a better sketch, we would need to know, for instance, the slope of the tangent line at that point, or at any one of these 4 particular points. Of course, here we see that there is probably some symmetry, so we only need to really find it at one point. At any other point on the curve, we might want to know what is the slope of the tangent line in order to be able to sketch a better curve. Also, we need to clarify what happens at the pole when we come back to the pole.